2. So therefore, let's look at it one more time. And more specifically, I can probably give some example. Yeah, let me open. Give me 1 second. Lecture. Was it lecture 14? No, not 14. Lecture. Yeah, okay. Okay. So recall this structure, right? So we talked about that structure some time ago. In last lecture, we also looked at it one more time. So that's the structure of the page table in x86-64. So we have this permission bits, we have this physical page number. So by the way, I think that was also one of the questions in midterm. What does the page table entry typically contain? So there was some answers. Virtual page number. Does it contain virtual page number? No. Virtual page offset? No. Physical page number? Yes. So that's exactly what we see here. Permission bits? Yes. So that's also exactly what we see here. I think there was some other funny answer like cache offset or something like this. So that was just yeah. So that's definitely also not part of the page table. So yeah, we have physical page number and we have permission bits. So recall that we have 12 lower bits are used for permission bits, and that's natural because we have 12 bits dedicated for the for the page size. So 2 to the power of 12 for kilobyte is the page size. Therefore, it's natural to use the lower bits to recycle for something else, something more useful. And that's what you do for in malloc lab as well. So if something is aligned, you don't want to put zeros there. You want to use these bits for something else if possible. So the same way it happens here. So you always point to the beginning of the page. So you can treat these bits as some sort of the same thing that you do in a malloc. So if you mask them out, you get the byte offset. If you leave them, you get physical page number plus permission bits. Anyway, yeah, so that's just the convenience. I mean, it doesn't have to be this way. Maybe we could have started with 0, but they decided to keep this lower bit so that you can always easily mask them if necessary. Yeah, so then you have upper bit, 63rd bit. This is used for non-executable permission bit, but this one is, so this one we will not actually use in our project. This is for security protection. So to make sure that you are not trying to execute some injected code, so that if you inject it on stack, if the malicious act injects it on stack, so that you don't execute it. So therefore, data can always be marked like stack or data pages. They can always be marked as non-executable. So this is just one, I guess, outlier here. And then there is some reserved bits from 52 to 62. They have to be set to 0. Again, available means set it to 0. Doesn't mean keep them as is, because if your CPU notices something that it doesn't support in these bits, and let's say accidentally you have some 1 in uninitialized memory area, therefore it will just crash and you won't even know what's going on. So please make sure you initialize everything. So maybe if you are in doubt, maybe initialize the entire page table with zeros first before you even touch any bits. So that way you don't have any uninitialized memory. Okay, so yeah, and then we have 52 up to 52 bits from 12 to 51st bit is the physical page number. So the physical address is 52-bit at most. As I said, in practice, it's actually less. I guess on my computer was shown 39 bits. I mean, I tested on a different computer recently, was shown 48 bits. Maybe it's a different Linux version also, showing different, bit widths for the page table. Also, so we have, so this is the physical address limits. So the physical address limits, so we can go up to 52 bits. So unless we change the page table format, that's the architectural limit. For virtual addresses, that is not the case. So we currently have 48 bits. Now there is an extension of 57 bits in some computers. I mean, potentially they can extend it out all the way up to 64-bit without changing the architecture. Okay, so this is just different levels, and you can look at these bits in more detail. But let us take a look at the actual implementation. So recall that we can define a page table entry as a bit field, like present bit, writable, user mode, page address. And then we can initialize these bit fields as though they were like a separate structure, variables. But this is really still the same 64-bit integer in the struct. So I actually, as I said previously, I don't recommend using bit fields in my I just showed it in the slide for illustration. It's probably going to make your code more complicated than necessary, because otherwise you just need to initialize the physical page number and maybe set a couple of permission bits, something like that. So it's much easier to do that using bitwise OR and just using the normal 64-bit integer. So just use that if possible. Also, it's less error prone because you will not leave any fields uninitialized. So with this one, it's just for illustration that we have this separate bits. Don't necessarily do that in your project. You can just use 64-bit integer, initialize these bits accordingly, like just do bitwise OR. At the end of the day, the compiler is going to generate the same code. There is no way you can modify an individual bit. There is no such instruction. I mean, there is some instructions, but they typically work on a register anyway, so not on memory. So therefore, the compiler will also generate some code which is used bitwise or bitwise and, so this is just going to be replaced by a compiler automatically. But you can do that better, I guess, if you just need to set a couple of bits, it's much easier to do it manually. So one thing that you will need to do in the project is to create an identity page table mapping. So, and it's not just identity, there will be some questions where you have to do something different. But the first thing, maybe what we want to do, we want to map our first 4 gigabytes of RAM. So we want to make sure that the kernel virtual address exactly corresponds to the physical address. So it's like if it's a virtual page number 1 corresponds to physical page number 1, virtual page number 2 to physical page number 2, and so on. So we want to create an identity mapping. Then later, the project also will ask you to do something somewhat different, but that's just a starting point. So how do we actually create an identity mapping? It's just the simplest page table that we can. By the way, the identity mapping is actually relevant. So I don't think it's just we are trying to simplify something and that's something that is not used in practice. For example, in Linux, it would, for convenience, in the kernel address space, it would map the entire physical RAM in certain region of virtual memory. So that no matter what process you are in, like as long as you're in kernel mode, you can always refer any physical RAM by just, adding some offset. So you map the entire physical RAM to a virtual region, to the dedicated virtual region. And then, of course, you have other virtual addresses that, like for the kernel, for user program, which may point to the same physical page, but that's different. So you just create an identity mapping somewhere in your address space. So that's a common practice in Linux. So therefore, it's not something unusual that we are doing here. So I guess the only difference here that we want to create an identity mapping, and we want to do it for kernel mode, so that the permission bit is set that it can only be accessed in kernel. So we kind of combine the kernel address space with the identity mapping. So that's what we are doing here. So it's kind of merging these two things together. In Linux, those are still separate. Here we're kind of merging it, and user space will be separate from it. So anyway, so let's just discuss how we can set up a 4 GB identity page table. Well, naturally, in every page table entry, you just need to refer to the corresponding physical page number. So if it's an entry that corresponds to virtual page number 0, put 0 there. If it's virtual page number corresponds to 1, like index is 1, put 1 there, and so on. So that's what happens on the last level. So last time it said, okay, we have 1 million pages because we have to accommodate, we have to map 4 GB and we have 4 KB pages. Therefore, it's not, it's obviously we have to have 1 million entries in the last level. And this is a contiguous range of addresses, so we don't have any gaps. I mean, obviously, after 4 GB, we don't need to map anything. After this, like a huge gap, but we just map the very first 4 GB. So what do we do? We start from 0, go to this 1 million, and just refer every page. So what should we put in page address? I put like I mean I didn't put the answer, but what should we put here in this loop? Page address equals to what? So page address is just a number, not the byte offset. So it's a physical page number. I'm sorry? Yes. So because this is an identity mapping. And so we have for PY index, page address equals to Y. For the last level, but only for the last level. So now let's see what's happening on other levels. So last level is simple. Just initialize it with the corresponding physical page number, and that's it. And in our case, it's easy because virtual page number equals to the physical page number. But now what is happening on a second level? No, this one. Oh, this one. So what is happening on so let us see what's happening on the second level. So the first level is easier. So the first level, the last level is easier, or level 1 in AMD terminology. So physical page, virtual page 0. Remember, just an index here. Virtual page 1. So there is nothing stored in the entry itself, but it's just an index. So that corresponds to physical page 0, physical page 1, and so on. So we have, how many pages do we have? So we have 2048 pages like this. So 2048. Why is that? Well, we have virtual page 511 here. So that's 512 entries in each. because we have 9 bits in each level. So that's going to be physical page 511. Then it's going to be virtual page 512, physical page 512, and so on. But we have to have 2048 entries. Why is that? Because if we multiply 2048 by 512, we get this 1 million entries that we need to map. And they are like it's a contiguous range that we need to map. So therefore we have to have 2048 entries. So 2048 pages. Each page accommodates 512 entries. So remember, right? So we have 8-byte entry size, 2 to the power 3. Page size is 2 to the power of 12. So therefore 2 to the power of 9 or 512 is the number of entries in each page. So now the second level. So the second level, so this is what they call level 1 in their terminology, or PTE, page table entries. Or PT, let me put page table entry. Level 2, it's called page directory. So how do we initialize page directory? So the second level. So now recall that this is gonna kind of point to the range of addresses, to the range of virtual addresses. So it's gonna say, okay, effectively this is from virtual page 0 to virtual page 511. Virtual page 512 to virtual page 1023. Right, so I mean, doesn't we don't actually write it. It's again, it's kind of implicit there. So all these addresses. So therefore, we're gonna kind of point to that page. By the way, some ask whether it's beginning. Yeah, it's always beginning of the page because I mean it's really page number we are referring, not the byte offset. So there's no beginning or end of the page or middle of the page because we are referring this the page number. So we point here, then we point this one to here. So this one doesn't point the real physical. So this one points to the real physical pages that you're going to use for the mapping. This one points to the physical pages, but of your page table, not of the mapping. Okay, go ahead.
In PTE, how are we able to loop over all like million entries? Like, why don't we have to construct each of the 2000 pages individually?
Well, yeah, so you can, this is kind of done, yeah, you can construct them individually, but if it's like say a contiguous array that I'm giving to you, like a large buffer, which can accommodate all these pages. So let's say I'm giving you 8 megabyte, by the way, it's a good question, right? We have 8 megabyte buffer that I'm giving to you. So how, if I have 8 megabyte buffer, how many pages can it fit? 2048 pages. Yeah, you can calculate that, right? So a 4 kilobyte page size, 2048, that's going to be 8 megabyte. So that's exactly 8 megabyte buffer. Let's say I allocated a contiguous range. It's page aligned in the beginning, and I just gave this buffer to you. So you just continuously initialize that till you reach the very end. So what will happen is that you will have this large buffer. That's your first page, that's your second page, that's your third page, 12th page. So you can just continuously go, this like 0, 511, 512, 1023. So you kind of can go uninterrupted, right? If it's a contiguous buffer. Does it make sense? What is your question? Oh. Yes.
So for the page directories, does the entry does it point to like the entire page table, or does it point to like the first entry in the following.
Yeah, I think the confusion here is, I think the terminology, let's not use PT because that's, the entire thing is a page table and that what they also call page table, right? Let's just, let me erase that PT, let's call it level 1, right?
So for each entry in level 2, does it point to like the entire table in level 1, or does it? Just
No, it points to the page, each entry points to the page.
It's-
Remember, each entry can only points to a page
Yeah,
because it's a physical page number in each entry that we store.
so each entry in level 2 points to the first virtual page.
No physical page,
Oh,
because page table itself keeps the physical addresses. I mean, the page table cannot depend on any other virtual addresses. So physical page table itself defined, the virtual address space. Therefore, it cannot depend on some other page table.
okay, so for level 2, like the first entry points to physical page 0.
To the physical page that contains entries, to the physical page of level 1, which contains entries from 0 to 511.
Okay. And then.
Second entry, you're gonna point to the physical page, which accommodates entry from 512 to 1023,
Okay,
and so on, right? Until we reach 1 million entries.
so each entry in level 2 contains like a block of.
Yeah, so it's a range of addresses. Remember that as we go further and further, we kind of deal with ranges, with large ranges. Here we dealing with individual pages in the last level. Here we're dealing with ranges effectively. So, and if we go further, we're gonna be dealing with gigabytes, terabytes, and so on. Does it make sense? Okay, what was your question about that?
Yeah, so. If we only have 4 pages in level 2. Why do we go from 0 to 2048?
This is 2048 entries. So how many entries we have on each page? 512. So the level 2 has the same situation. It has a contiguous buffer. This is level 1, right? So level 2 has a similar situation. It's contiguous buffer. I mean, you can choose, you can implement different. I just show a simple implementation. I mean, maybe you don't want to use contiguous buffer, but I'm just giving you a large chunk of memory so that, why not use contiguous buffer anyway? So in level 2, you will have first is going to be 0, 511, then 512 to 1023, then 1024 to 2047, right? So then we will have 1, 2, 3. I'm sorry, I'm kind of lost here. Give me 1 second. This is not 2047. We have what is this? 30. This is 512. 1023.
1535.
Yeah, I know. Yeah, 1024, 1535, and 5036, and then 2047. Yes, so something like this. Does it make sense? Yeah, so you have 512 entries in each of them. So you initialize 4 pages. Does it make sense or not?
Yeah, I think so. Thank you.
Yeah, so now the question is. So the question is, how do we determine what the address is of this stuff? So for this address is simple, it's just an index, because we just want to create an identity mapping for the last level. So remember, only last level or level 1, whatever it is, right? Only that level points to the real physical pages. Only this level. This one points to the physical pages of the page table, not of the mapping. So now, what do we have in level 2? we have to refer to the physical page, which corresponds to level 1. How do we determine this? So let's take a look at the second loop. We have this address. So we adjusted this address P plus 1 million entries. So look at the PDE, right? So it says how do we initialize PDE? So it's P plus 1 million entries. So we skip this large buffer and then go continue from that point, right? So we kind of continue on level 2 here, effectively. And we will keep continuing level 3 and level 4 after this. So this level 2 is really here. So this is where we start initializing the second level, right after level 1. So how do we determine what the each entry is? So we need to determine the starting address of the first level. So how do we do that? Because it's a range effectively, 0 to 511, 512 to 1023. So what we're gonna do, we're gonna have P is the base address, P is this. This is the P pointer. Plus 512 multiplied by J, and J is just the counter from 0 to 1047. So 512 on the first round it's going to be P. In the second round it's going to be in the second iteration when J is 1 is going to be P plus 512. That's exactly what we have, P plus 512. Then it's going to be P plus 1030 P plus 1024, right? Because 512 multiplied by 2. Then P plus 1536, P plus 2048, and so on. So this is just because the counter keeps changing. So 0, 512, 1024, and so on. So you multiply 512 by J. So this is the line when we calculate start PTE. So that calculates the byte offset, and that's the virtual address. So start PTE is the virtual address. But remember, in our model, we will just assume for simplicity that virtual address is the same as the physical address, just for simplicity. Therefore, we can treat it also as a physical address. Because remember, pointers are always virtual addresses. But we can treat it in this simple case as a physical address. But we don't need a byte address because it's a bit field. I mean, it depends how you implement it. If you implement it not per bit field, but 64-bit integer, you might just clean up lower bits. But because it's a bit field, we need to specify 40 bits with, with really page number. So what do? We take this byte address and right shift it by 12. That means also the same as dividing by 4096. So basically by the page size. So we divide by the page size. This is how we get the page number. So we shift it by 12. Again, if you have 12, if you don't use bit field, you have this 12 lower bits, you just need to clean them up. But other than this, I mean, by the way, it should be already 0 here, unless you have any bugs, so you don't even need to clean them up. So this is how we initialize the second level. And how many pages we have on the second level? How many pages do we have on the second level? 4, yes. So we have 4 pages, significantly less than the first level. Yeah, so now what is going to happen with level 3? So level 3 will have to point to this page, and this one has to point to that page in level 3. So now it's much bigger range of addresses. I'm not going to even calculate, but it's a much bigger range in each entry. so effectively in the third level, each entry addresses 1 GB of of memory. So at each entry, and we have 4 entries. So that's actually why we have 4 GB will be 4 entries exactly. Yeah, so now here we have to calculate the address of the page directory now, not of page table, and put the corresponding entry. Don't forget that you have actual 512 entries in a page, but we only use 4 entries in level 3. So what do we do with other entries? What do we do with other entries? So if present bit is set to 0, the page is not present. So what should we put there? Okay.
Everything besides the 4 entries.
Yes, yes. And that means that the present bit is 0. That means this page is not present. So that means there is no mapping. Remember, this is one advantage of multi-level page tables, that we can effectively just put zeros here, and we don't need to create level 2, level 1 for those entries. The moment that we put 0 here for the remaining entries, we are done. So that means this is large gap at the end, and we are not using the remaining address space. Because the address space, of course, is much bigger than 4 GB, but we are not using the remaining address space. So we're going to put 0 there. So now, obviously, level 3 can fit in 1 page. We are not even using the entire page, but we still have to use at least 1 page. So finally, level 4 is also going to be 1 page. But now it has how many entries? Just 1 entry. Because now it just points to that page and that's it. And then everything else is 0. Yeah, so this is how we can map 4 GB. So I'm not showing it for the third level or fourth level. It's just, just calculate it yourself. How do we need to calculate the address? So I've shown an example for the second level. Do the similar thing for the third level and fourth level. Just remember that now you point to level 2 here, and then level 4 you point level 3. So, I mean, that's kind of, I think, simple exercise, but oftentimes I know that people also have like, like in Malloc, maybe it's fundamentally not that complicated, but when you start implementing it, you have some, issues there, right? So it starts crashing, and you don't know why it's crashing, and so on. Yeah, so I think just start project too early, because don't put it till the last moment. Because I think project 2 is not complicated. Fundamentally, it's probably easier than project 1, but at the same time, and it's probably also to some extent easier to review the code. It's harder to debug the code because there is no GDB or anything like this for project 2. But it's easier maybe to review the code because there is not too much code to review. So if you have a bug, it's easy probably to find it. Okay, go ahead.
What do you mean we won't be able to use GDB?
Well, because we will use like low level, like basically we kind of run our own small operating system, and then you have to set up a page table there. So, and that doesn't support, of course, GDB, because it's very minimalistic system, which you boot in a virtual machine. So, but at the same time, what I did, I gave some, I will give you some so it's kind of like I'm giving you like hip checker, so to say, for the first project. Here I'm not giving you a hip checker for the first project, but here I will give you some checker of the page table. It will say, oh, you have a bug in this and that level, please fix it. So, and that way that part is kind of done for you, right? So, and that at least will prevent from setting up a completely buggy page table, so that you don't, it won't catch every single error, of course, but I guess 90% of errors it will be able to catch. So maybe in some corner cases, you will still see that you load the page table, it still crashes, but it's really kind of a corner case. Typically, you would still see a message that's what actually is wrong in your page table, and then you have to go back and see your code and fix it. So that I'm trying to help you with that. So even though we don't have GDB, but at least we have some, some verification tool which will help you to identify the problem. So it will, for example, say that, this entry doesn't look right, like maybe entry free 20 or something like this in your level 1 doesn't look correct. So then you're gonna go back in your code and see where you initialize it, and maybe add some printf statements to make sure that I actually see the expected value that that you're supposed to see. So printf you can still use, so you will still see the debugging messages on the screen. So we still have some debugging capabilities, just we cannot use GDB for project 2. Does it make sense? So I think that project 2 is fundamentally easier than project 1, but at the same time, there are some slightly different challenges. And therefore, if you start early, there is a possibility that you will be able to finish it early. And even long before the deadline. But at the same time, at least you will know, okay, I'm done with this project. I got this, I got this number of points. So please start early. This way you are on will be in much better position. Because it's better to finish it early and get it done, and then maybe do something else than struggle in the very last minute. Okay. Also, I think I will provide you with the aligned page. So I think I'll skip the last slide because I will already provide you aligned addresses. So it's probably not that important. Last slide. So you won't need to do any additional alignment. But by the way, how do you do alignment? Just can you? Any guesses? So if let's say I give you some address E, how do you make sure that it's 4 kilobyte aligned? Okay, go ahead.
Would you modulo by 2 to the 12?
Yes, but what do I need to do? I mean, I cannot go back to the previous memory. I can do modular, right? So, but let's say it's a starting address. I cannot go back before that. I can only go back further, but not before that. So I can skip maybe up to 4 kilobyte. I can waste that memory for padding, but I cannot go back. So what should I do before modular? So the typical strategy is that I will add the alignment number -1, which is going to be 4095. So if it's already aligned, then 4095 is not going to move to the next page. It's still going to stay in the same page. But if it was at least 1 byte off, that will go to the next page. So and then how do I determine? So I said next page, but how do I get to the beginning of that page? Well, at that point, I actually have this modular. So I have bitwise and. So again, assume that this is maybe casted to size t. E plus 4095. So treat it as an integer. Then what do you do? How do you do modular? You can do modular here like this. Modular 4096. Sorry, not 4096. Actually, I apologize. This is not modular here. This is actually we want to do bitwise AND operation. So it's not modular in the sense that we want to subtract modular, right? So effectively we have to do p minus this, but we can actually do a simpler thing. Instead of having p minus this number modulo 4096, we can have bitwise and then what? 4095 inverted. So why is that? Because we have 111 bits and then maybe zeros. That's what 4095 is. Like I don't know like how many ones we'll have, but it doesn't matter fundamentally. So then if we invert, we're gonna get 11111. This is gonna become 0000. So we're gonna clean up this lower 12 bits when we do bitwise AND. So bitwise AND, this is how we have ones in the variant 4095. And then if we do the NOT operation, we will get zeros there, and everything else is going to be 1. So that's a little bit easier than p minus, modular this, right? So that's just, that works for power of 2 numbers. It won't work in general, but will work for power of 2 numbers. Okay. Any other questions? So for the alignment, I don't think you will need to worry about this. I just kind of remind this, but because I will already give you a aligned address. So unless you want to do something else and want to align it for whatever reason, we won't probably need it. So I think the advantage of project 2, it's also that you are trying to set up a page table on a real architecture, on a real CPU. So I think that gives you some exposure to like a low level, programming a little bit. So you really see what's going on under the hood in the OS kernel. Maybe it's not complicated page table. I guess if you look at the kernel, Linux kernel page table is going to be far more complicated than what we're going to write here. But at the same time, it's just a simple example where we can when we can practice with the page table. And I think it's very useful. I actually found that many people, until they actually implement, don't fully understand page tables. They think they understand, but until they actually implement this project 2, they don't fully understand page tables. And I think that's what happens so oftentimes. So it's good to have that project. So let's at least get started on the next topic. I think we have all information we need for project 2, at least certainly to get started. And let's talk about some future topics such as libc and threads. So we have to get started on concurrency soon. But before we do that, we have to talk a little bit about OS abstractions such as threads. So just recall that system calls, just to remind you, what is system call? We can switching from privileged to unprivileged mode is not a problem. It can happen anywhere. Whenever the OS kernel decides to go back to use a program, it can do so. But switching from unprivileged to privileged mode is definitely not allowed to do to any arbitrary place. So we have to use it can only happen through traps or interrupts. So this is how we switch to kernel mode. So this special trap, one special trap is known as a system call. And each system call has a special entry point. So that's an address that is programmed in memory. So by the way, you will still have some system call, some small, I guess one question will be related to system calls in project 2. So that's also partially relevant for project 2. Even though we already covered that material, but there is something that will still be relevant. So each system call has a special entry point that's going to be an address programmed in memory. So you just say, okay, you can jump to that address. When you jump to this address, I'm prepared to handle any whatever request you have. But the handler that resides at that address will not actually trust any parameters. So it will say, okay, yeah, maybe you're a nice program, but I'm not gonna trust your pointers. Let me check that this pointer points to the valid memory. So it's just like you go to the airport, you go and everyone has to go through the security verification. So something like this will happen here. So you don't just jump to the plane right away. So the same thing happens here. You don't just jump to the kernel code that you want to execute right away. So you have to go back through this verification first. And some of this verification is kind of ongoing. So even when you're already executing kernel mode, I mean, it's actually a little more complicated because what if you had some page, but then you later unmapped it? So for that case, the kernel also accommodates it. So you have a special page fault handler, which will verify the range of addresses, but that's just a minor detail. So it may be somewhat slightly different from the airport model when they finished verifying you. So this kind of verification will be still ongoing. Some verification still be going on in the kernel mode later. But nonetheless, this, so this is, we enter for the special place. We don't just jump to arbitrary place. And at that point, some checks will already be done. So what we have in a real system is that, let's say I have an application, and this application maybe implements POSIX or any other standard that supported by the libc. So that will issue some function calls, and the function calls are going to be handled by the standard C library. So let's say it's a typical on Linux in system, it's a GNU C library. In the C library, you will have a whole bunch of different functions. So now some of these functions will directly translate to system calls that you have inside the OS kernel. For example, if you are issuing write to file, that's more or less POSIX write. That more or less, maybe not precisely, but almost the same way converts to the corresponding write system call in Linux. So on the other hand, if you have some other function like such as fprintf, that's a more high-level function that has some formatting, something like this. So part of this work will be done in the C library, so the formatting, and then eventually fprintf will issue the write system call, so more low-level call. Also, you have similar way, maybe like if it's some application that is not POSIX compatible, maybe Linux application, it also has its own Linux API. There is some function calls that are supported by the C library. But C library is somewhat an intermediate layer between the application and the operating system. Typically, I mean, even though you can do that, but typically none of the existing applications will talk to the OS kernel directly. Like you would not issue system calls directly. Even though it's possible, you can write this code, but typically you would still do that through the C library, and the C library will have a corresponding wrapper function, which will invoke a system call. So you have like around 380 system calls, probably nowadays a little more than this, and then 2000s functions in the C library. So those are more high level functions on top of the system calls. So mostly you have access to system calls, but then you also have additional functions. So you may wonder, why do we need libc? Well, obviously, we want to have some higher level functions such as printf, fprintf. We don't want to implement that in our program each time we write the code, but that's not the only issue. The other issue is that we want to write code which is platform independent. So imagine if I develop a program that only runs on x86 64, and I also have ARM machines. I have some PowerPC machines, maybe Spark machines, and so on. I want to write my program, compile it. Maybe I need to recompile this program on different Linux systems, but at the same time, I don't want to rewrite the program for using some Spark or ARM system call interface. So I don't want to be platform dependent. The C library will hide these details from us, so we'll just call a function in a regular way. And then obviously we don't want to use assembly code also in our C programs. We want to at least minimize that. Because system calls can be implemented, but typically they can only be implemented through the assembly code, not through the standard C mechanisms. So the API is also mostly platform independent. For example, this is a kind of different. So this is kind of different from previous one. So the previous one is about the architecture, the CPU architecture. So, but you may also have different operating systems. Maybe you run Linux, maybe you run NetBSD, maybe you run in FreeBSD, maybe you run in some microkernels. In some systems, you will not even use system calls, you would use some different mechanisms. And if you hide these details inside the C library, you can still compile programs in the systems. Also, if you want to replace some functions, for example, there is a way to substitute certain functions like malloc. You can substitute malloc in libc with your own memory allocator. So whatever you wrote, for example, you can replace the default malloc implementation in libc with your implementation. So you can use the LD preload mechanism for this purpose. So again, that libc allows you to do that. And whenever you have malloc, including malloc in libc itself, that will use a new version of malloc. So libc is more than just a wrapper for system calls, as I said, right? So this is, you have high level function. That's another reason why you want to do that. So malloc, again, malloc is a high level function. Malloc is implementing a memory allocator, which internally will use memas, which internally uses BRK or mmap, something that operating system understands. So let's run a simple program when we use printf and malloc. So you have three printf statements, you have malloc in between, and then you have free, and then just compile the program with O0. That's just to avoid any optimization. So use O0 to, if you want to generate some debug. I mean, not just debugging. I mean, debugging information is separate, but with O0, it may also be easier to debug. So let's run strace. Strace is the tool that allows you to catch what system calls this program is going to execute. So if you call the right system call, it should show that in the output. So now this is actually going to go not to your application, but whatever libc, like you're going to call libc function, and then eventually libc is going to talk to the OS kernel. So that last step can be actually monitored by the strace tool. So let's see what it will show. So it will show some system calls such as exec that you are executing test binary. It returns 0. That means it succeeded. And then at some point you can see that it opens a libc library which is located in this path, and it returns a file descriptor. So the free is the file descriptor. Then it calls mmap. Remember, the first argument for mmap is the preferred address. In this case, it didn't prefer any, I think, address, so it specified null. And then it also, remember, that it specifies the file descriptor in one of the argument. So it's going to specify free. So now this libc is m-mapped to the address space. Then you can see later on it closes the file descriptor after it mapped this file. Then we have brk. That's just initial setting, like we setting up heap initially. But then surprisingly, you don't see any mmap calls or brk or anything like this. So you have just printf statements. Before allocating, after allocating, after free. So you see printf at least were translated to the right system calls. So printf is a high-level function, right is the system call that's going to be handling that function. So you can also notice that there is a file descriptor 1 here. So what does 1 mean? Any idea? Yes. So you have standard input. This is 0. Standard out is 1, and standard error 2. So this is why the libc, the first file that we opened was file descriptor free, because from 0 to 2 is already taken by default by standard input, standard out, and standard error. So it puts to standard out this message. So in write system call specifies file descriptor, data that you want to write, and then number of bytes. It says that it returns also number of bytes that was written. So everything was successful, but we are not sure why malloc was not shown between before allocating and after allocating. Why didn't we see malloc? Well, because there is already some initial heap size, and we didn't actually allocate too much. We just allocated 1 kilobyte. So size is too small. So what if we increase it to 1 megabyte? So let's see what will happen. So now you will see something different in that place. So you'll see before allocating, now you see mmap, like anonymous memory, something that you saw in your project. So it calls memlib, calls mmap to extend the heap when you call mem as brk. So it will call mmap system call, after allocating, and then we had free. So free can also shrink the heap. I mean, we didn't have that in our project, in project 1, but if you are deallocating some memory, it's natural to also not just extend the heap, but also shrink the heap if possible. And in that case, it was possible, so that's why it was also unmapped in that region. So this is, again, this is how we translate C function calls to system calls. So take a look through strace. Strace can be really useful. I think it's good to see what's going on in the operating system. So map anonymous means it's not backed by any actual files. So we used mmap to allocate memory effectively. You can see that now the file descriptor in mmap was -1. So it means there is no file descriptor. So, okay, still have just a little bit of time. So what are the problems with system calls? Just in general. We talk about system calls, and it seems like a mechanism that is widely adopted by operating systems. But what are the problems with them? Well, the fundamental problem is it can, for example, easily pollute TLB. Remember, TLB space is limited. And if you access some addresses within certain range, you want to kind of keep this locality as much as possible. But if you are jumping from one part of your virtual address space to another part of your virtual address space all the time, then you can easily pollute your TLB. So maybe you will have some computational intensive calculations first. Then you have to issue some system calls, and that system calls will have to do something inside the kernel. That's a completely different set of addresses that you need to deal with. At that point, when you finish the system call, you have to go back, but maybe when you go back, you have to continue again working with that set you were working with previously, and you already kind of polluted TLB, so you have evicted this TLB entry, so now you have to bring them back, so you have TLB misses again, and that can cause this indirect cost of due to TLB misses. So TLB works well if there is some locality, but if you are jumping from user mode to kernel mode all the time, there is no locality anymore. Similarly, we can pollute cache. Kernel data and kernel data and code is different, so therefore, I mean, for the same reason. So this is completely different code set and data set. And also, there is a direct cost of system calls. So to execute a system call, to execute a special trap, you have to waste, I mean, at least I guess 100 cycles, probably more, even in modern CPUs where they're trying to optimize it. It's still, we are talking about some hundreds of cycles. And compare that maybe to some addition operation or subtraction operation, maybe it will take like one cycle, right, or something like that. So you're wasting a lot of cycles doing some just fundamentally executing some function inside the OS kernel. So, and not to mention that once you reach the kernel, you also have to do some additional checks. You have to verify these parameters. So this is certainly something to think about. You can see how people try to address this problem. For example, in FlexSC paper 2010, they try to replace system calls with somewhat different mechanism. And in this mechanism, what they did is that they would allow different execution entities inside the kernel. So typically you would run a separate task inside the kernel, and that can even be executed on different CPU, and therefore it will have a different TLB and different cache, and that would handle a request on behalf of the user program in this different task. So as long as you have many cores, you can basically eliminate this problem. Again, this is not something that is widely adopted in Linux, but this asynchronous or somewhat, I guess it's a synchronous model because you're asking some task to do something on your behalf, and then you go back to your task. Maybe you'll do something else in the meantime. But that's fundamentally the asynchronous model. But it can be used in many cases, but unfortunately, it's still kind of more like experimental or somewhat research oriented, right? So it's not still not widely adopted. But this is something that can eliminate this cost. So let's actually probably stop here because I don't want to start a new topic. Let's continue our next lecture.